This is number 15 from the chapter review, and we are told that we have 2 runners and we have a flagpole. And like I said, always draw the situation. These people run in a very odd manner, but you know, that's what you get. So we have runner A, we have runner B. We are told that runner A is 6.0 km west of the pole, so that's west, that's east, and runner B is 5 km Gesundheit, east of the pole. So the total distance between the 2 of them is 11 kilometers. Runner A has a velocity, and it's constant. They're a machine, apparently. So the velocity of runner A is 9.0 kilometers per hour. The velocity of runner B is 8 kilometers per hour. Okay. So what we want to know is when will they cross paths? Where will they cross paths? You know, will they cross paths here, or right? Will they meet at the flagpole? You know, that's what we want to know. So what we have to do is start to list everything that we know to be true about each situation. So for each of them, we know that they have some distance they're going to run. We know that they have a velocity which is described as constant. It's unchanging. There's no acceleration. There's no initial and final. They are just running. So we know that for something with constant velocity, that velocity is equal to distance divided by time. So the velocity of A is equal to the distance that A travels divided by the time it takes them to do it. And the velocity of B is equal to the distance or the displacement of B divided by the time. So that's one of the things we know. We also know that at whatever point they cross paths, no matter where it is, you know, whether it's here or here or here, the distance that the 2 of them will have covered together has to add up to the total distance between them. So we know that at the point when they cross paths, the total distance is going to be 11.0 kilometers. Is that true? Okay. We also know, so we have their velocity and we can find their displacements. Okay, so what that gives us is a side equation. And we do a lot of side equations in here. Let me shrink this up into the corner. So I'm going to write a little side equation here that just says that delta x of A plus delta x of B has to equal 11.0 km. And I just I'll pop it there. Well, what that allows me to do is solve for one of those. So I now have, we'll just do delta x of A is equal to 11, my writing is terrible, 11.0 km minus, I'm going to have to move this out in order to write on it, minus delta x of B. So what I've just done is redefined delta XA in terms of delta XB. So I now have an expression there that basically eliminates a variable because I've found the relationship between the 2 of them. At the point when they cross paths, they will have been moving for the same amount of time. Their times will be equal. So can we solve each of these for time? Yeah, we can. So delta t equals delta xa over va, and delta t equals delta xb over vb. We can probably shrink all of that. How did I miss the flag? Okay. Well, since we're saying that those times are going to be equal, then we can set this equal to that. So you can do this. Delta XA divided by VA equals delta XB divided by VB. Well, at this point, we have variables now that we actually have values for 3 of the 4. Well, no, we don't. We have values for 2 of them, and we have a way to eliminate one of them and get an expression for it. So what we're able to do here is we can take this and substitute this expression in. And we'll take this to the next page. Okay. So now we have 11. Oh. Okay, so we've got 11 km minus delta XB over VA equals delta XB over VB. So at this point, we have only one variable that we need to solve for. And it's some algebra to get there, but we can do that because we have values for V sub A and values for V sub B, and we can rearrange and isolate delta X sub B. Do you want a minute to do that? It involves factoring. Oh, that's the other thing that the math guys said is, well, algebra 2 is really lots and lots of factoring. I just remember the quadratic equation. You know, the thing that, and you check the answers, I'm sure, so you know this. They meet 0.2 km west of the flagpole. Oh, interesting. So page 58, number 1. Did you realize that the stroller refers to the stroller in the sample problem on the previous page?
Yeah, I figured that out.
Okay. That's helpful. So, yes it is. All of your other information comes from the problem on the previous page. Do you need me to do anything more? Okay, didn't think so. Good, strike that one. So we took care of those 2. We took care of that one. Number 5 and 6 on page 58. Oh, excellent. Okay, so we have another airplane. That's the worst airplane I've ever drawn. That's fine, it'll go. So liftoff speed is the speed that a vehicle has to achieve to get off the ground. So that would be their final velocity. Was that a wording thing? Did you not understand the wording on that one? Okay. So if an airplane is going down the runway, what's their initial speed?
0.
Yeah, VI is 0. VF is what we're looking for, and we need to compare it to that liftoff speed. Oh, no, we're not looking for that. I'm sorry. Sorry. We want to achieve a VF of 240. It's the kind of question where they very often, like I've asked similar questions where I say, okay, this is the liftoff speed. This is the acceleration the airplane's capable of. This is your runway length. Can you get it? Okay, so we have VA, we have VF, and we have delta X. What we need is the acceleration necessary. So you're just tying those 4 factors together. Which equation would that be?
The final velocity after any displacement.
Give me the fun equation. That's a sentence.
It's that one.
I'm just contractually obligated to give you grief, Ms. Warren. Okay, so yes, that's the one. Okay. Number 6, also on page 58, motorboat accelerates uniformly. Ooh, okay. The reason this is tough is because they're throwing in the east and west thing. So what you have to imagine is sort of a 0 line here which would be where you're going from an east velocity to a west velocity. So if they had an acceleration of 2.7 meters per second this away, and they end up, or I'm sorry, whoops, they had that's the velocity. They had an acceleration of 2.7 meters per second this way, and their velocity was 6.5 meters per second this away, and that was their initial, and their final was 1.5 meters per second this away for their final. What happened to them? They slowed down. So what you want to do is just treat this as a negative acceleration. We'll talk a lot more next week about using sign as a proxy for direction. Did you get that? Good. Yeah, so that's all they're doing is, this is like if you're heading north on 7 and you hit the brakes, you now have an acceleration to the south because your velocity is diminishing in a northward direction. Your acceleration is towards the south. Okay? That's gross?
Yeah.
Why is it gross? Like weird, confusing, I can understand. Gross, I reserve for things like, do you want to talk about slugs and the dual-gland adhesion system? Okay, fastest warship belongs to the Navy. It's a hovercraft. It moves along on a cushion of air, can move as fast as 1.7 times 10 to the second kilometers per hour. Suppose during training exercise the ship accelerates at, okay. So here's our hovercraft, moving on its little cushion of air. It has a VI, it has a VF, it undergoes a period of acceleration, and it has a displacement during that period of acceleration. So those are the four things we have to tie together. Which equation would we use to tie these together? Do you already have this one, Tarek?
Yeah.
Okay. Which equation will we use to tie these together?
We don't have delta x.
Oh, we also have delta t, I'm sorry.
Yeah, we don't. Delta x equals
Yeah, we do have.
t plus 1/2 a delta t squared.
We're being asked to calculate initial velocity. So it's one of the factors in there.
So will the final velocity be 1.7 times 10 a second?
Oh, wait a second. We don't have final velocity, do we?
Nope.
No, I'm sorry. That's what we don't have. That's what we don't have. So we have delta t, a, delta x, and we want vi. What do we want to use? Oh! You know what? Who got this already? How'd you do it? Which equation did you use?
Delta x equals vi delta t plus 1/2 a delta t squared.
Whoops.
That was like way too fast for me to process.
Delta x equals vi delta t. Oh, you know what? Because we have delta t. I'm sorry. I'm thinking there are a few. If delta t is non-zero and you need to find delta t, you can't use this one without using the quadratic. That's what I was thinking of. But no, we have delta t, so it doesn't matter. And I hate the quadratic. I'm on record as saying that. Okay, and we are looking for VI. So, straightforward rearrangement. Delta x minus 1/2 delta t squared equals VI delta t. Divide both sides by delta t. We get rid of this. The temptation is to go, oh, okay, this cancels out the delta t. This does not have a delta t factor in it, so be real careful. You're better off to just leave it like that. Okay, does that jet-powered car had a VI? It had a VF. We know what the delta x was. We have skid marks to prove how far it went while it was undergoing this negative acceleration. Acceleration was negative 2.00 meters per second squared. What was its initial velocity? Well, we've got VI, VF, A, and delta x. So which equation would we be using? And I should list these down the side. What's VF? 0, because it's coming to a stop. Delta x, and of course we'll have to convert that 9.60 km and acceleration of negative 2.00 meters per second squared. Okay. And VI is our question mark. So what are we using?
F squared minus 2a
Oops.
delta x.
Yep.
That's squared.
Yep. You don't, well, yeah, you have to do a little bit of rearrangement, but not much. And that's it. Okay. Anything, yeah, it's a trick stapler, sorry. Anything else?
Can I see the equation for 2b after you rearranged it?
This one?
Yeah.
Do you see why?
Yeah, I still.
Okay.